Hello, welcome to this video, and today we're going to look at a physics problem which will be able to solve using polar coordinates, which I recently did a video about. So let's look at the problem. So we have a mass m and a ring with radius r on a table. So this drawing is a view from above of our system. And it starts with an angle of theta 0, and with a beginning linear velocity v0. And we also know that the table where this mass m and the ring are all sitting on is completely smooth. No friction there, but where there is friction is between the mass and the ring, with the kinetic friction coefficient being mu. So mu is the friction, okay, and now we need what we want is to find theta, and to find the angle theta the mass will make in terms of the time that passes. So let's begin. And so let's begin, and what we're going to do, because this is a mass that goes in a circle, we're going to look at this problem in polar coordinates. So let's look at the forces in the radial direction, which is this direction, and then in the tangential direction, or the theta direction. So Fr has all the forces acting upon it in its radial direction, and the only forces acting on it in this plane are actually friction and normal force. And the only thing acting in the radial direction is the normal force here. In the opposite direction, and this is negative the normal force. It's coming from the ring. But we also know, by Newton's laws, this is mass times acceleration in the radial direction. And we also know the formula for the acceleration in the radial direction. It is, so this is going to be mass times, so the radial acceleration is r double dot minus r theta dot squared, where r represents the radius, theta represents the angle. But we know that this mass m spins in a circle where the radius is constant. It doesn't break the ring or somehow go inside the ring. Meaning that if our radius is constant, our double dot, which represents the second derivative with respect to time of the radius, is 0. Meaning that this is negative mass times radius times theta dot squared. Meaning that our normal force is mass radius theta dot squared. Now let's look at the tangential direction. So in tangential direction, which will represent this. And so if theta is going to be, theta is in this direction, but the only force we have in the theta direction is the friction force, which goes this way. Represent it as F, meaning that this is negative F. And F, because the mass is moving, it begins with velocity v0, meaning that it begins when it's already moving. Meaning that our friction is kinetic friction, meaning that it is equal to normal force times the kinetic friction coefficient, aka negative mu n, which is negative mu mr theta dot squared. But again, we know by Newton's second law, this is mass times the acceleration in the theta direction, and we also have a formula for this. This is mass, so it's going to be mass times the formula for the tangential acceleration, which is which is 2r dot theta dot plus r theta double dot, where again r represents the radius, theta represents the angle. But again, because our radius is constant, our dot, which is the derivative of the radius with respect to time, is 0. Meaning that this is mass, radius, and then theta double dot. And now we could do some simplification. So let's cancel out m times r, and we'll get, if we cancel out m times r, we'll get theta double dot is negative mu theta dot squared. Now we will use the counterweight to symbolize theta dot, which is omega for the angular velocity, meaning that the second derivative becomes the first derivative of omega, and theta dot becomes just omega, and this is the equation we get. Now this is a differential equation. But before we go on solving it, because we want omega with respect to time, and then we'll integrate to get theta with respect to time, we need to find the initial omega. But we know from the formulas of polar coordinates, omega times r is equal to v. Omega, the angular velocity, r, the radius, v, the linear velocity. And so, if we just look at it, when the time is 0, we get omega 0, which is the initial angular velocity, is v0 over r. So this is the initial angular velocity, and now we can go on and solving this differential equation. So let's mark it like so. So omega dot is just the derivative of omega with respect to time, and now we will do the thing that physicists are best at doing. Ignoring mathematical formality and looking at d omega and dt as constants. So let's multiply by dt and divide by negative omega squared. And we'll get negative d omega over omega squared is equal to mu dt. Now let's integrate. So here, because our d is of omega, we have d omega. We need it to be from omega 0 to some final omega. And because we can't reuse our omega. So omega can be our parameter here, called omega prime squared. So that's integrating this side, and then this side is similar. The beginning, time is 0, until time is some number t of mu, and because we can't reuse t as the parameter, it's going to be dt prime. Now, this is the integral of a constant, and so it is just the constant times this minus this, which is t, and then this is integrating this is like integrating negative 1 over x squared dx, and the derivative and the function that will give us the negative 1 over x squared as the derivative is 1 over x. And so this is 1 over omega prime from omega 0 to omega. Meaning that this is 1 over omega minus 1 over omega 0 equal to mu t. And so 1 over omega equals mu t plus 1 over omega 0. But remember, omega 0 is v0 over r. So this is 1 over this, aka r over v0 plus mu t. And I'll move this up here. And we'll get that omega, so the angular velocity with respect to time, is, let's quickly write it like so, r plus v0 ut over v0. And now 1 over this is going to be v0 over r plus v0 omega t, and finally mu t. Okay, we found the angular velocity with respect to time. Now let's just integrate this to find the angle with respect to time. And so let's move down here. And so integrating with respect to time here will get us theta t minus theta at the beginning, which is theta 0. This equals the integral from 0 to t of v0 over r0 plus v0 mu t prime dt prime. And again, I'm using t prime and not t because t is already one of the bounds in the integral. I can't reuse it as suddenly the parameter. Okay, now let's erase some of this, and then we'll be able to calculate quickly this final integral. Okay, let's calculate this final integral. So now this is going to be a simple integral. Let's do a u substitution of the bottom. And so du is going to be v0 mu dt prime. And so we'll get, this is the integral. If we plug in 0, we get r. If we plug in t, we get r plus v0 mu t. This is going to be of, now v0 dt prime is du over mu. So this is going to be, so because 1 over mu is a constant, I'll take it out of the integral, and we'll have left du over u. Now this is going to be natural log of the absolute value of u, but because everything here is positive, this is just going to be, in our case, natural log of u. 1 over mu times 1 over u from r plus v0 ut, and this is 1 over, it's not 1 over its natural log of u, 1 over mu. Now, natural log of this minus natural log of this is is the same as natural log of this over this by logarithmic rules. So this is 1 over u times natural log r plus v0 ut over r. And then finally we'll add theta 0 to get that the angle with respect to time is equal to the initial angle at theta 0 plus 1 over mu times natural log of r plus v0 ut over r. And that's our final answer. And the end of the problem, which you can think of the problem as an example of how to use differential equations in physics. Because that's what we did here. We looked at the forces and then we eventually got a differential equation hidden in the problem. And then we solved it and got an answer that seems completely unrelated to our initial problem, but yet is the correct solution. And finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. And finally, that's it.